Readme Revenge was a pwnable challenge at the 34C3 CTF, and in the end 30 teams solved it. Difficulty easy-ish? You can't own me if I don't use libc, right? We can download the binary here, and this was the IP and port to interact with the challenge. When I read the title, I knew immediately I had to try it. You see, 2 years ago, at the 32C3 CTF, there was a challenge called just readme. Back then I tried to solve it, but failed. After the CTF was over, I looked at the write-ups from other people and tried to understand it and even made a video about it. And 2 years ago, I did not have the skill, knowledge or experience to solve it. So when I saw that there is a readme Revenge at the 34C3 CTF, I just felt like I had to solve it. It was my personal challenge, and in some way it was very close to my heart. It was a challenge I failed 2 years ago, and now I can prove to myself that I improved. So let's have a look at it. Like I said, the challenge reminded me of this older challenge, and I assumed it was pretty similar. And it was easy to verify. For that challenge, you didn't have to get code execution, but the flag was actually embedded in the file. And if you look at the strings of the binary, you can see a placeholder flag. So the binary running on the server contains the real flag instead. And that is also where the name comes from, readme. Your task is to read or leak this flag from the target binary. The solution of the original readme challenge was super creative and really blew my mind at the time. So I encourage you to watch it because I had that knowledge in the back of my mind when approaching this challenge. So while it was obviously not the same challenge, it was a revenge of the readme challenge. It was similar in many ways, so I had a pretty good idea already. But let's check it out. When we run it, the program waits for input and then greets us with, "Hi LiveOverflow, bye." So it just reflects what we write. I immediately checked for format string vulnerability and entered a format string modifier like %x, but it didn't do anything. I also just tried a long input, and to my surprise, I immediately got a seg fault. Well, that's a good start. Let's look at it in GDB. So I run the binary with the long input. FYI, if you don't know why my GDB looks so colorful, it's because I used pwndebug GDB extension. But there was my second surprise. The binary had all the symbols still included, so we get all the function names. That's neat. So where did we crash? We got a seg fault in Printf inside of libc. To be more precise, in parse 1sec, I don't know. That's weird. The instruction that caused the seg fault is a compare where it calculates an address based on RAX and RDX, and RAX is clearly overwritten with A's. So I tried to access bad memory. But in libc? Does this mean printf of libc has a buffer overflow vulnerability? Well, we will see. Let's have a look at main. Disassemble main. It's super short. We have a scanf to read in a variable called name, and then we call printf with that name. There's a small but important detail here with the variable name. Usually, local variables are placed on the stack, so they are referenced as offsets from the stack pointer. Makes sense, right? But in this case, the variable is stored at an offset from the instruction pointer RIP. This means it's not on the stack if it's an offset of the instruction pointer, so an offset to the binary itself. This means it's a global variable stored in a data segment. You can see here GDB has already calculated or resolved this address for us. RIP at this point would be this address plus this offset here, so hex 6B73E0. And if we look at the virtual memory map of this process, we see that this address is in here. It says it would be heap, but I'm not sure why it says that, because I'm pretty sure that's not a heap. If we look at the sections defined in the ELF binary with object dump, we can see that the address belongs to BSS, which is used for statically allocated variables. Anyway, let's go back to the crash. If we look now at the location where name is stored, we can print the memory. Here we see that there was a bit of a size allocated for the name. However, we wrote much more A's than that. Because we have all the symbols, we can also see which variables we have overwritten. So we overwrote DL static DTV array, no idea what that is. We override DL lazy variable. I mean, we have killed a lot of stuff. And apparently libc printf referenced something from in here. We have a very clear buffer overflow, and we overflow global variables, and many of those variables are libc internal variables. The binary was statically built with libc, which means the whole libc functions are part of this binary. That's the reason why those variables are part of our binary data segment. Usually, when dynamically referencing and loading libc, these variables would be located in the dynamically loaded libc memory. Anyway, here we have found the vulnerability. So how can we turn that now into reading the flag from memory? Clearly, just blindly overwriting data doesn't work, so let's do this systematically. I wanted to carefully control what I overwrite, so let's take a snapshot of the memory without an overflow. To do this, I set a breakpoint at the end of main, then I rerun it with a small input, and then I print the memory starting at name in 4-byte or 32-bit chunks. I just keep enter pressed until I reach the end. So now I can get a huge list with all the memory and the symbol names. Then I copy the whole thing into Sublime and use some text editor hotkey magic to quickly reformat this data. I'm removing all the pwn-debug prompts, making it all Python comment, and then taking the memory value. In the end, I want to rebuild the whole memory with the correct values. So I will use a buffer variable where I will append the raw bytes. And in a second, I will define a new function b32 that will convert this memory value to raw bytes. I can do this with import struct and then struct.pack with a capital I for 32-bit values. I will also create a function b64 because we have a 64-bit binary, so might come in handy as well. So now this Python script prints the whole memory. Cool. Theoretically, if we use this to overflow the buffer, it will overwrite the memory with completely safe values. Basically not changed anything. And indeed, it seems to have worked and we didn't get a seg fault. But now comes the true challenge. What do we overwrite that could help us to leak the flag from memory? Well, I didn't know. In the old readme challenge, we smashed the stack cookie in a buffer overflow on the stack, which executed the stack smashing detection function. That function would print the program name, and the program name is referenced from a pointer on the stack, and so overriding that pointer with the same overflow on the stack with the address of the flag caused the flag to be printed when the stack got smashed. So I kept that inspiration in mind. So I was just going through the symbols one by one and tried to find one that sounds interesting. DL static DTV, slot info list, DTV gaps, TLS generation, domain binding, cat counter, exit function called, prefetch multiple threads, debug. Nothing immediately jumps out to me. Oh, libc argv and libc argc. So there's a pointer to argc and argv as well. I keep that in mind. The old readme challenge also used an overflow of the program name pointer to point it to the flag, so might be useful again. This all means nothing to me. Nothing screams, hey, I print your flag if you change me. But then I reach the printf function table, and function table always screams, change me and you can redirect code execution. But why is there such a thing as a printf function table? If we look up this in the libc source code, we can maybe learn more about it. A comment here says, array of functions indexed by format character. And in here is also a function called register printf specifier. So if we Google for that function, we can quickly find that there's such a thing as customizing printf. The GNU C library lets you define your own custom conversion specifiers for printf template strings to teach printf clever ways to printf the important data structures of your program. The way you do this is by registering the conversion with the function register printf function. Let's read up a bit more about this. The function takes a spec, a handler function, and an arginfo function. If spec is capital Y, it defines a conversion for %capital Y. You can redefine the built-in conversion like %s, and the handler function is the function called by printf in France when this conversion appears in the template string. The arginfo function is the function called by parse printf format when this conversion appears in the template string. That sounds perfect. Our printf template string contains a %s. If we somehow could redefine the conversion for %s, we could define our own handler function and could execute any code we want. I mean, we can't really call register printf function, but we could maybe override and modify the underlying table directly. If we look again into the source code of the register printf function, we can maybe figure out how it would work if we want to redefine %s. So we would pass in a small s as spec and would give it a function as converter and arginfo. And down here, it simply uses spec as an offset into printf function table and printf arginfo table. That sounds easy. We know there's a pointer to the printf function table in memory that we can override. So we could point it to some other memory. And that memory should then have a function redefined at the array position small s. So that would be offset hex 73 or entry number 163 in decimal. Cool, let's try that. First, let's look for some memory area we could abuse for this. Let's try here, dl static dtv, let's hope it's not important. So now we want to override the printf function table to point there. Let's try it out. We write that into a file, set a breakpoint in GDB and use the file as input. Now let's see the memory. Oh, it's not there, but it should be there. This is the stuff that could drive you crazy, but you need to chill and approach it logically. So the overflow happens because of a scanf. The scanf used %s to read input. So let's check out the main page of scanf. The scanf family of functions scans input according to format as described below. S matches a sequence of non-white space characters. The input string stops at white space. Aha! So maybe our memory dump contains some white space. So what are typical white space characters? Of course, hex 20, a regular space, is a white space character, but also new line would be a problem, and basically all of these. So hex 09, hex 0a, b, c, and d. So let's make sure that these can't occur in our buffer. I just add a few lines of code to replace these with a regular capital X. Let's try it out. Oh, sec fault. Okay, we clearly did something now. Let's check out the memory in GDB. And yup, there is our value. But wait, that's not quite right. Why 58 at the end? Oh, our address had a space too. Well, good we caught that. So let's point it at 24 instead. Cool. Next we want to try to set a function for %s. So from our new table address, we have to get the array entry for ASCII value s, which is hex 73, which means we have to take that times 8 because we are on 64 bits, so each array entry, each function address is 8 bytes wide. Cool, so let's go to that address and write there a test value. Let's see if we successfully redirect code execution. We run it with the input, but sec fault. Let's look at the code Y. It tried to calculate RCX plus RDX times 8. Hey, that looks almost like what we just calculated. RDX is also in fact the hex 73, so the letter S, but RCX is 0. So this calculation points to bad code. But why is that happening? Didn't we override the function table entry with a value? It shouldn't be 0. But if we look at the disassembly of this function, we see that it references the arginfo table just before it. Ha, we didn't modify that. So once we pointed that to the same address, we can try it again. Both tables should be okay now. Let's rerun it with that, and we get a sec fault at a call RAX, and RAX is the value we wanted it to be. Awesome. So what to do next? I first thought about pointing it to printf, and maybe we can somehow control the first parameter too, based on how this printf modifier function is called, but then decided to use the technique I have learned from the old readme challenge, using stack check fail. Let's get the address of that function. That could work. But to print the flag, we also have to control the program name pointer and point it to the flag. But remember, there was some kind of argv pointer in there too. Previously, it pointed into the environment variables on the stack, so let's just point it somewhere else here. And this is now a list of argument string pointers. And so the first pointer has to point to the program name, so we point it to the flag instead. This is the address of flag in the file. I'm excited. Will this work now? We piped the exploit output into readme revenge, and boom, stack smashing detected. And here's our flag. So what we did was, we overflowed the printf modification table and redefined what to do when printf encounters a %s. Upon finding the %s, it took the address of our modified function table, which pointed to stack check fail instead. That function is then executed and gets a program name to show it in an error message. But we also modified the pointer to the program arguments, argv, and pointed the program name, which is the first argument, to the flag. So the error printed the flag. And here is a screenshot from when I did that during the CTF to grab the real flag. Printf is so fun sometimes. I'm so proud of myself, because this really shows me how much I've learned in the past 2 years and how I improved. Back then I would have not been able to solve this, but now I did. Pretty straightforward. Makes me feel really good.